Okay. So we have here our next topics. We have cycles and cyclic notation, subgroups, and integral domain. Okay, cyclic notation. We all know that cyclic notation is another form of permutation. The cyclic permutation of A1, A2 to AN, A2, A3 to AI as the cycle decomposition of A1, A2, and AN. This permutation is a cycle of length n. So to understand this further, we have here some examples. So nagamit na their numbers 1, 2, 3, 4, 5. And below that, we have 3, 5, 4, 1, 2. So the next process will be getting the cycle decomposition. So mag-start from 1 map to 3. So if mahuman na nato siyang mapping, ato siyang i-cross out ha, pero dili na ko siya ma-cross out din eh. Ay wait. Ako sang ikuan. Okay, let's try that. So 1 is mapped to 3. Okay, ito i-cross out si 1. Muna naman siya. 1 is mapped to 3. And 3 is mapped to 4. 3 is mapped to 4. And 4 is mapped to 1. So, dili man siya pwede. Dili siya pwede. So, ang atong wait. Okay. Dili siya pwede. So, we have here our first cycle. 1, 3, and 4. And we're going to multiply that to our second cycle. So, ang mga remaining numbers, mo atong i-map na pod. Muna naman yung 4. Okay, so we have 2 mapped to 5. And 5 is mapped to 2, so nagbalik-balik siya. So, ang atong second cycle will be 2 and 5. So, that will be our cycle decomposition. Okay, cycle decomposition. Okay. So that is our first example. So we only have the 2 cycles there. Okay, example number 2. We have 1, 2, 3, 4, 5. And below that, we have 2, 4, 3, 1, 6. So we're going to start from 2, okay? Mapping by 2. Okay. Nag-cross-out siya. Okay, so we have 2 is mapped to 4, where 4 is mapped to 1, and 1 is mapped to 2. So, mauna siya ang atong first cycle. Dili siya. Okay, so our first cycle is 2, 4, 1. And we're going to multiply that to our remaining numbers. So we have here 3 is mapped to itself, and ato siyang i-separate into a single cycle. We have here the single cycle 3. And actually 5 din siya. 5 din siyang koan. Kani 5. Okay, that is 5. So 5 is mapped to itself. And we have there the third cycle, the single cycle 5. So our cycle decompositions in this given equation is 2, 4, 1 times the single cycle 3 times the single cycle. Okay, so let's proceed to cyclic groups. A group G is a cyclic group if there exists an element A is an element of G. The element A is called the generator of group G. Okay, for example, the group G equals -1, 1, I, negative I is a cyclic group since I is a generator. The generator S3 is not cyclic since it has no generator. Okay. Notice that the set S2 equals the set of 1, 2, and below that we have 1, 2, and we're going to divide that by 1, 2, and the reciprocal, which is the 2, 1. And so this is a group with respect to multiplication. Okay, so notice the table below. Based on the table, furthermore, the group is also cyclic because the cycle 1, 2 and 2, 1 is a generator of the group. So, maato siyang generator, di ba? Okay, let's proceed to transpositions. Okay. Okay, we must take note that a cyclic of length 2 is called a transposition. Every permutation can be expressed as a product of transposition. The following illustrates the transposition property. Okay, so A. We have here 1, 2, 3 equals the single cycle 13 times the single cycle 12. So it is equal to the quantity of 1, 2, 3, 3, 2, 1 times the quantity of 1, 2, 3, 2, 1, 3 equals 1, 2, 3, and it is mapped to 2, 3, 1. Okay, letter B, we have here the cycle 1, 2, 3, 4 equals the single cycle 12, single cycle 13 times the single cycle 14. So we have here the cycle 1, 2, 3, 4 mapped to 2, 1, 3, 4 and 1, 2, 3, 4 mapped to 3, 2, 1, 4 times the cycle 1, 2, 3, 4 mapped to 4, 2, 3, 1 equals the quantity of, the cycle 1, 2, 3, 4 mapped to 4, 1, 2, 3. Okay. 1, 2, 3, 4, 5 mapped to 2, 1, 5, 3, 4 equals the single cycle 12. Single cycle 354 equals the single cycle 12. Single cycle 34 times 35 equals 1, 2, 3, 4, 5 mapped to 2, 1, 3, 4, 5 times the cycle 1, 2, 3, 4, 5 mapped to 1, 2, 4, 3, 5 times the cycle 1, 2, 3, 4, 5 mapped to 1, 2, 5, 4, 3. Okay, we must take note that a permutation is even if it can be expressed as a product of an even number of the permutations. Okay. The permutation is odd if it can be expressed as a product of an odd number or an odd number of the transpositions. So for example, we have here 1, 2, 3 is even permutation. Ano naman siyang even? Ano naman siyang even? Okay. Kay 1 is mapped to 2 and 2 is mapped to 3. So, duha lang, diba? Duha lang ka mapping diha. So, that is even permutation. And we have here the second, the odd permutation. We have here 1 mapped to 4, where 4 is mapped to 3, and 3 is mapped to 2. So, as we've noticed, diba, tulo ka mapping diha. So, that is an odd permutation. Okay. Second example of an odd permutation. We have here the single cycle 12, 3 mapped to times 3 mapped to 5, and 5 mapped to 4. So we have here tulo ka mapping kay ang 12 is mapped by itself. Mo siya ng nice single cycle. Okay, let's proceed to subgroups. Okay, we must take note that if H is a non-empty subset of group G, then H is a subgroup of G if H is a group under the same operation G. Okay, remember, H is a subset of G. H is a group. H and G as the same binary operation. Okay. So we have here G equals a cycle of Z positive. H equals 5Z positive. And we have 5Z equals 5N, whereas N is an element of Z equals all real numbers from negative all real numbers. So we have H is a subset of G, H is a group, H and G is the same binary operation. So ato man ang take note ganiha, di ba? Okay. Therefore, H is less than G. Integral domain. So in integral domain, we have zero divisors. We're going to talk about zero divisors. So if A, Hammond's product of B and A is not equal to 0, then we call A and B as zero divisors. Okay, for example, in Z4, as in the table, okay, notice the table below. We have here 1, 2, 3, 1, 2, 3, 2, 0, 2, 3, 2, 1 times, we're going to get the Hammond's product by multiplying that numbers in 1, 2, 3. So we have here 2, the Hammond's product of 2 equals 0, but 2 is not equal to 0. Thus, 2 is zero divisor of Z4. Okay, let's have another example. Find the zero divisor of A, Z6, B, Z12, C, Z3, and D, Z. Okay, solutions. In Z6, 2 Hammond's product of 3 equals 0, but 2 is not equal to 0 and 3 is not equal to 0. Thus, 2 and 3 are zero divisors. Okay. Integral domain is a commutative ring without zero divisors and with unity. Unity is the identity of for the second operation. Example. Okay. Show that Z3 is commutative ring. Solution. We have here closure. So, Z sub P is closed based on the table. For any A, B is an element of Z, whereas A plus B is an element of Z. This means that upon performing the operation to any elements of Z sub P, we cannot find any other element in the table except the elements of Z sub P. Another reason is for Z sub P to be closed under that elements of Z sub P are integers, and Z, the set of integers itself, is closed under the ordinary addition. Okay, let's have the second. Associative. The operator direct sum is associative since the elements Z sub P are integers and the ordinary addition is associative under Z. Number 3, identity. The identity direct sum is 0 for any element Z sub P, whereas A plus 0 equals 0 plus A equals A. And we have here inverse. Notice element 1. 1 plus 2 equals 2 plus 1 equals 0, whereas 2 is inverse of 1. Element 2, 2 plus 1 equals 1 plus 2 equals 0. 1 is the inverse of 2. Okay, let's proceed to commutative. The operator direct sum is commutative based on the table. This means that the elements are symmetric with respect to the main diagonal. This symmetry implies commutativity under the operator direct sum. Closure. Z sub p is closed with respect to Hammazard product. This means that for any elements A, B, Z sub p is an element, whereas A, Hammazard product of B, is an element of Z sub p. The closure property under Hammazard product can also be based on the mere fact that the elements of Z sub p are integers and Z is closed under multiplication. Associative. The elements of Z sub p are integers and the ordinary multiplication is associative under Z. Thus, Hammazard product is associative under Z sub p. Okay, H, distributive. The distributive property is implied by the mere fact that it holds under the set of integers. Thus, for any elements A, B, and C is an element of Z sub p, then we have A, Hammazard product times B plus C equals A Hammazard product of B times A Hammazard product of C. There's Z sub p plus the direct sum, and the Hammazard product is a ring. Commutative. The operator Hammazard product is commutative since the elements are symmetric based on the main diagonal. Thus, Z sub p is commutative ring. Zero divisors. Z sub p contains no zero divisor. This means that A times B equals 0 will only happen for A or B is 0. But we cannot find other integers A and B in Z sub b satisfying the property. Okay. So we have A Hammazard product of B equals 0 and A is not equal to 0 and B is not equal to 0. Thus, Z sub b contains no zero divisor. Okay, unity, the unity of Z sub b is 1. Okay, for all A is an element of Z sub p, whereas A Hammazard product of 1 equals 1 times A equals A. Okay. Thus, Z sub 3 is an integral domain.